What? So chapter 18, sources and control of pre-analytical variation. So working in a lab, you guys are going to be in charge of, you know, your lab results. So some samples might get like, you know, rejected, and that might have to do with the pre-analytical variation. What does pre-analytical mean?
Before tests or testing.
Yeah, before testing. So what kind of things happen in pre-analytical stages? Collection. Transport. And even before collection, you got the patient, right?
Identification.
Yeah, patient identification. And then even then, you know, they could be I can't say that word, prandial. Do you know what that means? Postprandial? or preprandial? Do you know what that means? A lot of analytes have postprandial rises. One specifically is glucose. That's the most common one. What's postprandial? I don't know if I'm saying it right.
Are you talking about like some of them are higher in the morning?
That's not prandial variation. That's.
We're talking about the one if they're upright or.
No. No. Postprandial is like eating. Yeah.
After dinner or lunch.
Yeah.
Thank you, Google.
Anyways, we'll go on. So first we'll talk about the whole testing cycle. You've got your, like we just talked about this, your pre-analytical cycle begins with the patient, right? And it's going to end with the preparation of the sample. So that's what we're talking about today, is this pre-analytical variation. Then you have the analytical, and that's what we'll be doing in the lab, although we're also in charge of collecting the samples, or we're responsible, not really in charge. So the analytical section includes all the steps involved in performing the laboratory, all the steps involved in performing the laboratory test. Okay? And then you have your post-analytical phase, and that begins reporting the results to the healthcare provider. So, and then it ends with the action taken by the healthcare provider. So the whole phase then. So errors in the testing cycle. 2002, a review was reported where the vast majority of errors occurred during the pre- and post-analytical phases. Less than 13 to 32% actually come from the analytical phase. So the majority of errors are either pre-analytical or post-analytical. Fewer during the analytical phase. But when you have errors, that invalidates the link, right, between the test results and the patient state. Because if you have some sort of errors, you're going to get faulty values. Maybe you won't be able to catch some kind of diagnosis, or you will. And the ultimate goal of healthcare is to what?
Figure out what's wrong.
Yeah, improve the well-being of the patient, or the, what's that called? Goodness of life, not goodness of life. Huh? Quality of life, there you go. Sorry, I'm bad at words.
My word's not good.
So, standard procedures to minimize the sources of errors are developed by laboratories. So that's where you'll have these SOPs for everything, right? Because they're going to be standardized procedures. And hopefully if you follow those SOPs, you'll have fewer errors, right? Can you do that? Follow SOPs? And then accreditation agencies require detailed manuals that are going to have all these standard procedures in them. Do you guys know what accreditation agencies are? More or less, yeah. So they're agencies. They're not really governmental. They're non-governmental agencies, but they accredit labs. The government requires you, like a clinical lab, to be accredited. So they have to seek accreditation by these outside. There's like several examples, like the CAP is one that you'll hear a lot about, and I forget what it's called. I knew before class. but it's something of pathologists.
I think we do CAP, like, studies every few months or something. They send us something and we have to like do it and send them back.
Yep, and that's what that is. Those are, I can't remember any words today.
I'm working on it.
I think it's College America, huh?
This is actually kind of hard to figure out.
Yeah, because I'm sure there's lots of things for CAP, but it's like College of American Pathologists or something like that.
Yeah.
And they test, they send you stuff, like she said, you test it and then send them the results, and then they tell you how well you did, like next to the mean compared to everybody else. It's like group testing, and you're compared, and if you're so many standard deviations away from the mean, then you fail that test, and then that can be bad. Okay, so pre-collection causes of variation. So the test order processing. So college, look, I have it right here. College of American Pathologists found 3.5% of outpatient test orders had errors. So just the orders themselves were errors. 1.4 tests were ordered, 1.4% of tests ordered weren't performed, 1.1% wrong test is performed. Inpatients had similar results, 1.9% of the tests ordered not performed. All orders were processed manually with no physician order entry system. So I think these days at the hospitals you go, they have everything computerized, and the physician has to enter stuff. So that's one way they minimize the errors with the computer systems. And I'll try to get into that chapter this semester too. Uh-oh. So, but here's a big variable in your analytes, is just cyclic biological variation. What is cyclic variation? Anybody have any ideas? Right, yeah, it's a cycle. Cyclic variation. So things that go up and down are in a circle, right? So there are changes in the concentration of analytes that occur in predictable fashions at certain times of the day, week, or month. Anybody think of any? Huh? Menstrual cycle every month, right? That's a good one. And that'll change a lot of analytes. What's the one you ever heard of, like cortisol? Yeah, but then there's
Isn't the one that's more accurate or more active during the night?
Yeah, yeah, and that's all that, like cortisol is also like one of those that follows that. So, but what's that cycle called? Circadian, yes. So those are what we're talking about. And these are the like cycles of change. So we can contemplate something. We get pre-contemplation leads to contemplation, which leads to determination, to action, to maintenance, to relapse, and the contemplation again, or it could lead to lasting change. So this has nothing to do with the lab testing, but these are comparisons in prey and predator populations, right? So that follows the cycle. You get an increase in prey, which will cause an increase in predator, but that increase in predator will cause a decrease in prey, which will cause a decrease in predators. So they all follow these cycles. The first one we'll talk about is circadian cycles, the most reproducible cyclic variation, right? So one thing you need to know about patients who are having analytes that may vary with circadian rhythms is if they're on, if they work nights, that they might have reverse circadian rhythm, basically, right? If they're up all night and sleep all day normally. So blood concentrations of most pituitary hormones rise at night and fall during the day. Likewise, hormones whose concentrations are affected by pituitary hormones show similar diurnal changes. And that's what this is called, a daily change is a diurnal change. Okay? And this shows you how not having enough sleep can disrupt your diurnal hormone. So this is thyroid stimulating hormone. If you only get 4 hours of sleep in bed, it shows a variation like this, whereas if you have 12 hours of sleep, 12 hours in bed with 9 hours of sleep, you get like nice peaks and troughs throughout the day. And that leads to altered leptin concentrations. Anybody know what leptin is? Has to do with metabolism, in mammals at least. So it's like, they discovered it, I think, in mice. You can knock out leptin receptors, and then they I forget now. But leptin, it controls basically appetite. So I think if you have a lot of leptin, it reduces your appetite. But if you don't have it, you'll have a bigger appetite. So in this study, if you get less sleep, you'll tend to eat more, right? Does that make sense? So anyways, that has nothing to do with us. It just is an example to show you circadian rhythms affect all kinds of different analytes. And getting enough sleep does too. So sodium, potassium, phosphate, all of these concentrations in the urine may vary by as much as 50% at different times of the day, right? And urine is one that'll vary greatly. There's a lot of things that can cause urine concentrations to vary, right? What can make you think that could cause urine concentrations of analytes to vary?
Drinking a lot of water.
Exactly. Drinking a lot of water, you're going to have dilute urine. So a lot of times, do you know how they collect urine if they're doing a urine study?
Do it first thing in the morning?
Well,
Is it a bed, is the patient bedridden? Because they use catheters to exertion into the bladder.
yeah, but for most urinalysis studies, you're going to be doing a 24-hour urine sample. So you'll have a patient empty their bladder at the beginning of the test, and then they'll have a bucket that they have to pee into for the next 24 hours. And then you then they empty it at the end of that 24-hour period, and you have it. And rather than calculate concentrations of things, you calculate, the whole volume you have of your urine, and then you can calculate the amount that was cleared in the urine. And one of the analytes you've heard of creatinine, right? And so creatinine clearance is basically is used as a measure of glomerular, see, there's my word problems again. Glomerular filtration rate, right? It determines that everybody should clear a certain amount of creatinine per day. So, anyways, both serum and urine levels of osteocalcin and collagen telepeptides can differ by 50 to 100% between peak and trough values. Test specimens should only be collected at certain times, and reference limits should be based on those collection times. Do you guys understand what reference limits are? We got a whole chapter coming up on reference limits. And this book throws things at you before we ever introduce them. So basically, reference intervals are like for the most cases, 95% confidence interval of a whole population. So, and that's what they use as the limits. The reference limits typically. Unless there's some kind of disease state that can clearly be defined, they'll separate the diseased and the healthy. But for normal healthy individuals, the reference limits are the 95% confidence limits of the mean values, or the median values. Right? It's not everything's normally distributed. So for things that vary a lot based on time of day, you need to collect those analytes those times a day. This is a figure from your book showing you Ultradian variation. And this is more than the diurnal variation. What am I doing? I don't know why I did that. So diurnal variation is like throughout the day, like big changes. This is like a lot of little changes all the time. And this shows you pituitary changes. Here's your diurnal change. You got a big peak, and then you wake up in the morning with really low values, and then a big peak right before bed. So that's your diurnal variation. But then the ultradian variation are all these little peaks and valleys. So it's like very variable throughout the day. Does that make sense? Difference between ultradian and diurnal? Okay. Infradian variation. So what do you think that means? That's variation that occurs for periods that are longer than a day. And you already gave me an example of that. The menstrual cycle, right? So menstrual cycle is an example that causes monthly fluctuations in ovarian hormones, also calcium, magnesium, cholesterol, parathyroid hormone, renin, aldosterone, and antidiuretic hormone can have the same. This is a graph showing you the menstrual cycle and concentrations of all the different hormones and how they're affected based on that time of the month. So if you're checking for these, it's good to know what part of the cycle the patient is in too. Then circannual variation, what do you think that means? Seasonal, right. So we live up here in the Great White North, so we're going to have lower vitamin D levels in the winter, right? Maybe not us, but in Canada or Alaska, right? So analyte concentrations that are related to seasonal changes. Vitamin D is higher in the summer than it is in the winter. Urinary oxidase is also higher in the summer. So this shows you a graph. Vitamin D production in the body varies month and by month in Boston, Edmonton, Bergen, Norway. So Boston is the white circles. So you get a lot more in the summer in Boston than you do in what? Edmonton is the white squares, or Bergen, the black triangles. So Boston gets the most variation, but they all drop down to like nothing in the winter for all these cities. So different cities. I imagine Norway is probably the furthest north, isn't it? So random fluctuations also occur. Most analytes will show less than 5% intra-individual variation. What do you think that means, intra-individual variation? Do you guys remember intramolecular forces or intermolecular forces? What's an intramolecular force? Within the one molecule, right, is intramolecular. Intramolecular is how the molecules interact with each other. So an where am I? Intra-individual variation are variations within one person. So for most analytes, that's going to be less than 5%. So typically that's pretty normal. Substances such as bilirubin, creatinine kinase, triglycerides, and steroid hormones can have over a 20% day-to-day variation, however. So there's a check they do on patient analytes, and it's based on this 5% for the most part, and that's called a delta check. Have you heard of that? That's one of the quality controls. I think that's in this chapter. A delta check they do, where they do repeated samples for the same analyte from the same patient, and they look for big changes that could be, a big change in that could either be a change in the patient's state that needs to be looked at, or problem with the equipment. So they do delta checks as part of quality control. Then there's also patient-related physical variables. Regular aerobic exercise can decrease plasma muscle enzyme activity. So in the muscles, enzymes that we test for are going to be creatinine kinase. What do you guys think that does? Creatinine kinase. Add phosphates to creatine to make creatine phosphate. If you remember in the muscle, creatine phosphate is like an energy store. It'll transfer that phosphate from creatine phosphate directly to ADP to make ATP. So you won't need like real fast energy source in the muscle. So this is a marker for muscle activity, and there's different isozymes of creatinine kinase that can distinguish heart muscle from skeletal muscle. So we'll see that later on. Aspartate aminotransferase. This is an enzyme that takes the amino group from aspartate and transfers it to another alpha keto acid to make a new amino acid, or actually it's taking the amino group most likely from glutamate and giving it to the alpha keto acid of aspartate to make aspartic acid. And alanine aminotransferase does the same thing. From glutamate transfers the amino group to make alanine. Where do you think you find these? So these are commonly referred to as AAT and ALT. So these are often enzymes that are leaked from the liver when you have liver disease of some sort, or liver damage. So they're like the liver enzymes you always hear about. But I think there's with some heart disease you can find some of these also, but these are mostly liver markers. So you also see decreased markers for inflammation and coagulation with regular aerobic exercise. I guess that's one of the reasons why regular aerobic exercise is good, right? The inflammation is bad for us generally. Strenuous exercise, however, like strength training, can cause increase in plasma muscle enzymes and increases in uric acid and bilirubin. And that's because strenuous exercises, you're really ripping those muscles, and they'll leak the enzymes into the blood. Short-term intensive exercise, such as a marathon, you'll have increased potassium, uric acid, bilirubin, and muscle enzymes, and decreased glucose and phosphate levels, and that makes sense. And a lot of times before a patient has their blood drawn, they need to fill out a little questionnaire, and you'll ask them questions like this if they've been doing that, because you need to know if they just ran a marathon yesterday or the hour before they came here. So you'll see questions about exercise on those. And this is something from your book showing you just the figures. Effective exercise on laboratory test results, and they did this with 750 medical students, exercise versus no exercise, looking at uric acid, AST, and creatinine kinase. So AST is aspartate aminotransferase. So diet-related changes, most changes are transient due to diet, because you eat it, you absorb it, and then it gets distributed and then cleared from your blood. So they're easily controlled. And that's what this is the word, right? Postprandial or postprandial. Increases in sodium, uric acid, iron, and LD, lactate dehydrogenase, right? And then increases in hormones in response to eating also show a rise. So of course, once you eat, typically you're going to see an increase in insulin, and you'll see increases in gastrin too. Do you guys know what gastrin does? Or do you remember? I might have talked about it a little bit in biochem, because it's one of those pre-pro hormones that gets cleaved and then activated. But it's the hormone that causes your pancreas to secrete, or your stomach to start secreting acid, and pancreas to secrete the enzymes. So. Interfering substances can be found in food. So vanillin interferes with assays for vanilla-mandelic acid, so got to be concerned about those. Serotonin is going to increase 5-hydroxyindoleacetic acid. Meat, iron, and horseradish can also affect stool occult blood tests. So, because you'll get a lot of that iron there. All of those are containing iron. Horseradish contains a lot of iron. Do you know why? It's got that horseradish peroxidase enzyme in there, which requires iron. Stress. So mental or physical stress can alter many laboratory tests. Stress induces adrenocorticotropic hormone, cortisol, and catecholamines. Patients in intensive care units experience suppression of production of pituitary hormones and aldosterone. So elective evaluation of endocrine function and lipid status should not be performed during hospital admission for some other cause, just because that can be stressful, right? So do you want to And that'll throw off those results. Posture can also alter analyte concentrations. Upright posture causes increased hydrostatic pressure, resulting in water and electrolyte leakage from the intravascular compartments. Right? Does that make sense? So we're standing upright. We got a lot of hydrostatic pressure. So you get things that are going to pull in the body, right? Your fluids will pull in your legs. So you'll get increases in plasma concentration of proteins. Hemoconcentration, if you get more hydrostatic pressure, you're going to lose water to the interstitium, which will concentrate your blood, because those cells and things can't be concentrated. So you can get 5 to 8% of blood if it's drawn from a patient that's not been sitting for at least 15 minutes. So typically, when people are going to get their blood drawn, they have to be sitting for at least 15 minutes. And this can produce clinically significant differences in serum calcium, cholesterol, and lipoprotein concentrations. So procedures to minimize pre-collection errors is improve order processing accuracy, which includes this physician order entry system. Second person to review the computer entries also, because we know physicians aren't the albeit best experts on everything. They make plenty of mistakes in the hospital that, you know, you guys will have to catch too, right? Minimizing patient preparation errors, complete patient history, clear instructions for the phlebotomist and the patient on what needs to be done when you're collecting. And biological cyclic variation, diurnal affected test samples should be collected shortly after waking while still fasted, and ultradian affected tests should have several samples collected over a usual cycle. So, and then you test the area under the curve, which is what the AUC stands for, over time. So, physical variables, you want to inquire whether the patient is engaged in strenuous exercise in the past 24 to 48 hours, and specific dietary guidelines for patients prior to sample collection. So, has anybody ever done one of those glucose tolerance tests? No? I know when you're pregnant you have to do it, because it's pretty gross. They give you a recipe for this super sugary shake, and you have to drink it and then go to the lab and they take your blood an hour later. Because you take a certain dose of sugar and then you got to test your blood glucose, see how well you respond to that blood glucose. And they do that for pregnant women to make sure they don't have, you know, the diabetes that pregnant women get. There you go. I don't know why I'm so bad at words today.
A 3-hour glucose test if you don't like pass the first one or something?
Probably. Yeah. Or maybe it is 3 hours to begin with.
No, I think the first one
is just an hour?
Like the hour, if you don't pass that one, you have to do the 3 hour.
Yeah. Blood collection can also cause variation. You get, so they're the most common cause of erroneous test results. Non-laboratory staff with limited formal phlebotomy training have significantly high rates of sample rejection. And when I say sample rejection, the chemistry machines you see, they'll reject samples due to certain things. And a lot of those might be related to the collection. Can anybody think of one? See, you're in hematology now, right? What's one bad thing about collecting blood? When you mess up collecting, what does that cause?
Hemolysis.
Yeah, hemolysis. It's going to cause a lot of hemoglobin to be in the liquid part. And that hemoglobin absorbs light. A lot of the tests revolve on absorbing certain wavelengths of light. And if you got hemoglobin in there, it's going to absorb and interfere with that. So the chemistry machines themselves will see a certain amount of hemoglobin and get rid of it. Can anybody think of any other things that might be in the blood that will absorb light? Based on disease state that'll cause, I don't have it up there. I don't think we talk about it yet.
Think you have lipemic blood? Lipemic
blood, yeah. That doesn't absorb light, but it scatters it. And that's because if you eat a big fatty meal, this is a postprandial rise. If you guys remember, you eat fat, your intestines make those chylomicrons and kick them out, and those are in your circulation. Those chylomicrons are huge, big enough to scatter the light. So if you have a lot of chylomicrons around when you're checking your blood, you'll get that. And another, later on in the semester, I got a picture. When you separate the cells from the plasma or serum, it looks like milk when it's lipidic, and you can't read that because there's way too much light scatter. So that's one. There's another big one. So the hemolysis, lipidic samples, and the last one are the most common reasons that the machine will reject your sample. You might not get this last one though, because it can be associated with certain disease states. You know, and for you drinkers in here, you might end up with this disease state one day. Or at least Hemingway wrote about it in Farewell to Arms. He ended up with alcoholic hepatitis. Yeah. So you guys know what some of the symptoms of hepatitis are?
Jaundice.
Yeah, what causes jaundice? Is it lack of iron? Yeah, bilirubin.
Bilirubin, sorry. That's right.
Bilirubin. You can't break down the bilirubin, so you end up with that pigment, and that's called icterus samples, icteria or whatever in your sample. So your sample will be all yellow, and that absorbs light also, so that'll cause samples to be rejected. So CE by laboratory personnel and feedback and causes of rejected samples and oversights has been shown to reduce errors. Anybody have an idea what CE is? If you're going in the medical field, you'll get used to what CEs are. Yes, continuing education. So, and the laboratory personnel have to give continuing education to the people who are the phlebotomists and whatnot, nurses. A lot of nurses will take samples, so you got to continually educate them on how to collect samples properly. So. Blood collection techniques. So a lot of times evacuated tubes and specially designed needles are used, allowing simultaneous puncture of the vein and the tube stopper, most commonly used for collection. So things like this, where you have this tube with a needle in it that you stick the vacuum tube, and the vacuum tube's already got a vacuum in it, so it just draws the blood sample directly into it. So a lot of times they'll use a line that's connected to this that they'll insert IV, get it flowing, and then use this to collect the tubes. Glass tubes used to be, they were traditionally used, but you know, those are bad. Why? Because they'll break, and then they'll cut you, and then you have blood and broken glass from the patient, and now your blood, so it's bad for, you know, safety concerns, right? Many tubes are coated with silicone. Stoppers can be made with rubber though, and some rubber, like plasticizers, for example, this one, TBEP, is a plasticizer that'll leach into the sample, and it has been shown to cause problems when you're doing therapeutic drug analysis, where you're analyzing the concentrations of drugs in a patient sample, right? What this will do, it'll displace protein binding sites that the drugs are normally bound to. So it'll appear that the patient might have a higher blood concentration of it, or if this interferes with the protein binding sites, and then that drug diffuses into the erythrocyte fraction, so it'll make the concentration less. Does that make sense? In the plasma. When you separate the erythrocytes from the serum or plasma, you'll have a lot more in the erythrocyte, so it's kind of taking some out of your plasma pool. Does that make sense? So displacing from the protein binding sites. So blood can also be drawn into a syringe and then transferred to the tubes, but that can be a problem for safety reasons for the phlebotomist, and it also can increase the likelihood of hemolysis, right? When you're working with those needles and sucking, and then you'll see. We'll we'll be taking blood from each other. I always see hemolyzed samples from a few people. Skin puncture. So poor venous access might require skin puncture for blood collection. We have special microtubes are used which contain anticoagulants, and they're filled by capillary action. We'll be doing a lot of this because rather than draw blood from the vein, it's easier to prick our fingers and get enough that we need for some of our tests. So we'll do that a lot. And we have these little glass capillary tubes that are coated with heparin. You guys know what heparin is? Yeah. And this shows you the proper place of where to use these. On an infant, you want to use this part of the feet, and on fingers, you know, not directly in the middle, but off to the side, kind of. And what kind of blood are we getting from skin puncture? Capillary. And that's another variable of analytes is going to be from where it's coming from. Arterial, capillary versus venous. So depending on what analyte you want to test, what do you think the difference would be? So arterial blood will be what? It'll be oxygenated, have more nutrients in it and whatnot, whereas venous blood should have less oxygen, of course, and more waste products, less nutrients, so things like that. And this is a figure showing you a specialized heparinized capillary tube that has like little metal filings in it that you can stir the sample, keep the sample stirred with a magnetic. I've never seen one of these, but maybe you will in the lab. And that just keeps it mixed until you can go analyze the sample, I guess. Sources of sample, and here we are. So arterioles, best used for evaluate the delivery of substances to the tissues, because you know that's before the tissues take it up. You want to see concentration in arterial samples. Venous is going to have lower concentrations of substances used in metabolism, higher waste concentrations. And then capillary is closer in composition to arterial, except for the oxygen concentration. PO2 is going to be less in capillary, because that's where you get exchange. Anticoagulants used in phlebotomy can cause errors also. So if anticoagulants are used in plasma, it's collected rather than serum. We already talked about that last time, right? The difference between serum and plasma. You guys remember it? Huh?
Fibrinogen.
Fibrinogen, yeah. Plasma has fibrinogen, serum doesn't, because serum you let clot for at least a half an hour before you separate from the, you know, the cell fractions. Serum lacks fibrinogen. Platelets will release potassium during clotting also. So you might have higher potassium levels in serum than you do plasma. Phosphate concentrations are also lower in plasma. And in general, serum and heparinized plasma are used interchangeably though. So these are some of the minor changes. But some things to be considered are heparin treated patients. What kind of patients normally take heparin?
Prone to stroke or heart attacks.
Yeah, prone to stroke or heart attack. So if you have somebody prone to heart attacks, what are you typically looking for?
Clotting.
Yeah, or clotting. Well, so you're going to treat them with heparin to prevent clotting. So they're going to have heparin in their blood when you take it. And if you're doing a serum sample, is that going to affect your clotting time? Because typically they let it clot for a half an hour. If you have heparin in the blood already, it's going to be minor concentration increase if they're delivering heparin to the patient, but still it's there. It might increase the clotting time and you get incomplete clotting, and then you can get some fibrinogen forming in the serum itself, which will tie up some analytes. So like I said here, it'll delay the clot formation, and it can trap antibodies that are used for immunoassays, causing false high. This is creatinine kinase MB and troponin. Anybody remember what troponin is? You know, it's part of that muscle, right? It responds to the calcium. Troponin C, troponin I, and troponin, they're all together, and they block those actin binding sites on the, you know, so yeah, on the myosin. Or on the myosin binding sites on the actin. Let's see, I forget biochemistry after a couple weeks. So it's recommended that plasma is used for measurements of cardiac markers rather than serum. And that's because a lot of cardiac patients are going to be on heparin, right? So you want to use plasma instead. But plasma itself can interfere with some of these too, and we'll hear about how the anticoagulants interfere. So heparin will interfere. Heparin's used as an anticoagulant. Heparin can displace thyroxine from its binding proteins, falsely elevating the free thyroxine results. Anybody know what thyroxine is? It's like a thyroid hormone, right? So this will, so you don't want to test for thyroxine from a heparin tube, heparinized tube or heparinized capillary. So lithium and ammonium are cations. They're used with heparin to coat the, you know, they're like the counter ions with the heparin. Heparin's very negative. And that'll contaminate the samples for those results. So if you happen to be testing for lithium or ammonia, you don't want to use heparinized tubes because you're going to have high levels of those in the heparinized tubes. EDTA, who remembers what EDTA is? I know you guys have taken methods 1, or before methods 1 there was intro where you actually make the tetraacetic acid. So what's it, why do you put it in those like TE, for example? It's in TE. What's the purpose of it in TE?
TE is a buffer.
Yeah, but tris is the buffer part of that.
I'm just going through. So
yeah, it chelates. What does it chelate? It chelates calcium. A lot of enzymes need calcium to function, or magnesium to function. So they throw a lot of EDTA in there that'll strip all of those enzymes of any of the cofactors they need. So it works so you don't have any enzyme activity. And that's exactly what it's used for as an anticoagulant. It binds up all your calcium, and you can't get, you know, fibrinogen to be cut into fibrin. So you won't get those fibrin fibrils to form. So it prevents, you know, proteolysis. So it chelates divalent cations and results in inactivation of a number of enzymes, resulting in vitro changes to lipids, nucleic acids, and peptide hormones. And also, if you're testing for the enzyme, a lot of enzyme assays like those AST, ALT, CKMB, those are actually enzyme activity assays a lot of times. So if you have EDTA, it might strip it'll interfere with the activity of the enzymes you're testing for. So those EDTA plasma samples are no good for those, which results in falsely lowering colorimetric assays for these analytes. And it'll interfere with enzymatic assays that require cations also. Sample tubes containing EDTA should be drawn last, and that's just so you don't contaminate the samples that are drawn, you know, after them with EDTA. So errors related to serum separator tubes. We have, remember the other day we have swinging bucket and fixed angle rotors. So serum separator tubes, do you guys know what those are? They're like a convenience. Like, I don't know if you remember in methods 1, you're doing the separation, extraction, phenylchloroform extractions, you have to take the aqueous phase away. These aren't separated by phases so much, but they have separator gels in the tubes that are different density between the cell layer and the plasma or serum. So if you put the blood in there and then you spin it, you'll end up with the gel separating the cell from the serum or plasma from the cells. So it makes it easy so you can draw all of that plasma or serum out without worrying about grabbing any of the cells. Okay?
So they would just like shake it, like 8 times take the blood.
Yeah.
And use like the purple top too.
So you want to use a swinging bucket type for those though, because otherwise you'll get that gel at a strange angle. And so because if you're using the swinging bucket, you'll have a nice round portion, you get good separation. But if you get it at an angle from a fixed angle gel, you won't separate it as well. So you might have some cellular contamination then. So some agents, however, they can absorb to the separating gel and give you falsely lowering the concentrations. Recentrifugation of the tubes with separating gels can lead to an artifactually high potassium results. And also, there can be tourniquet-related errors. So why do we put tourniquets on when we're going to collect blood?
So you think the veins popped up?
Yeah, so it dilates your veins. You restrict the blood flow out of the organ, or not organ, limb, and it's going to cause those veins to swell up. So it makes it easy to find the vein and get it. But you shouldn't be drawing, it increases the venous pressure, right? Which is also going to force some of that fluid into the interstitium, which will falsely concentrate your hematocrit and concentrate proteins and things like that, right? Does that make sense? So the stasis induced by the tourniquets can result in predictable changes in lab tests. Increased pressure induces loss of water and electrolytes, which to the extra cellular fluid space, and this results in increased protein cells and substances bound to cells and proteins. So, and then this is a little study they did that they found actually that clenching falsely increases potassium, plasma potassium levels. So this is a study where the black one is a patient and then all the white spots are just different people who weren't patients, and they all did the tourniquet, and then they clenched, and then you get this big increase in potassium after clenching. Whereas if you don't clench, you don't have any increase in potassium. It's fairly level. So another thing. So clenching and leaving tourniquets on while you're drawing the samples are supposed to be bad, although it makes phlebotomy easier. So hemolysis. So it's the rupturing of erythrocytes and the release of their contents into the surrounding fluids. That occurs due to difficult connections, collections, unsecure line connections, contamination, incorrect needle size, as well as improper tube mixing, and incorrectly filling the tubes are all frequent causes of hemolysis. I used to hemolyze my samples all the time. But I was trying to, I was using pipetters and poking rats' eyes. It's hard to get, you got to go behind their eyeball and you puncture, and that's the way. And then the tail veins are really hard to get too. So. But I've never drawn from a real person. So. Huh? You have?
Yeah.
Yeah. We have to see it.
Yeah.
It sucks. It's scary.
It is not scary.
So, hemolysis can cause inaccurate lab test results by contaminating the surrounding plasma contents. Red blood cells, concentration. Oh, so parts, you get increased, the concentration of potassium inside red blood cells is much higher, so you'll see increases in potassium. And also the absorption you get from hemolysis will interfere with tests. Intravenous fluid contamination. What do you think this is? So if you're in a hospital, almost everybody's tied to an IV, right? So what are the things they get in those IVs?
Biofilms.
Huh?
If it's an infected or septic, you can biofilm.
You can get what?
Nothing, talking to myself.
Oh.
Intravenous maltophilia.
Huh?
That likes blood, likes IVs.
Who?
Intravenous maltophilia.
What is that?
It's the bacteria that likes to form biofilms on blood drawing equipment.
Oh, biofilms, yes. Well, you might see that, but that would be bad. But what we're talking about.
You asked, what is that contamination?
Well, no, that's not the kind of contamination. We're talking about analyte contamination. So what do people normally get IV? Glucose. So if you draw a sample of blood from the same arm that they're receiving the IV fluids in, you can get elevated concentrations of glucose or potassium, sodium, because it's diluted with the saline. It hasn't mixed with your whole blood yet. So that's what we're talking about with IV fluid contamination. So blood is collected from indwelling catheters or vena puncture without following the proper procedures. And the results from blood collected that is contaminated with IV fluids, we'll see a sharp increase in substances contained in the IV, such as glucose, heparin, and other drugs. So. Errors in patient and sample identification. This is the most common problem you see in the lab, is patient identification, where you don't have the proper specimen identification with the, you don't have the specimen identified with the patient. So that's a big problem. And what do you think the most common cause of that problem is? Yeah, the phlebotomist doesn't label the tube right as they take it. So study of blood banks found that 1 in 165 of samples had inadequate labels. The wrong patient identification occurred 1 out of every 2,000. And the most common error is when the phlebotomist fails to label the specimen before leaving the room. So label those specimens, or have them label the specimen. That's the most common error. And a lot of times you'll see these chain of custody forms where you have to, have positive specimen identification is required at every step. Collection, transport, and analysis, because you could get them mixed up too.
Objective, not fully complete.
So, procedures to minimize phlebotomy-related errors. Normally under direct control of the laboratory, should work closely with phlebotomy nursing physicians to develop clear written procedures and guidelines to minimize the errors. And these should be included for each test in the laboratory manual. Again, you're going to have this manual full of standard operating procedures. Type of specimen, the volume needed for the blood, the type of blood needed, arterial, capital, venous, and also the kind of tubes you're going to be collecting them in too, right? Patient identification, accurate identification of the patient before collection. Children or adults with mental illness may require picture IDs. If they can't communicate who they are, there's going to have to be some way to verify who they are, right? A lot of hospitals use barcodes these days, and they match patients on wristbands, and then you got to scan it, scan the tube, and do it all, so it makes it easier that way, right? Preservatives and anticoagulants. So because some of the, remember EDTA should be drawn last because you don't want to interfere. Glass tubes drawn without any anticoagulants or additives should be drawn first, right? That are basically for whole blood. And a lot of times you need to draw blood for coagulation testing. Do you guys know what coagulation testing? I know some of you have done it. Did you do that in blood banking or immuno?
Blood banking, we didn't actually get to do it.
You didn't get to do it?
No, because they only have blood banking once a week, so you can sit out for 24 hours.
No, I thought they have the little.
The shaker?
No, they're like a machine that stirs and you.
Yeah, we did do that.
Oh, yeah.
You time.
Is the clotting test?
Well, yeah, I guess that's
Yeah, you're right, yeah.
You measure the prothrombin time, right?
Isn't that hematology?
Is that hematology? Okay. So you guys will do that this semester.
Yeah, like when you wait till it pulls the magnet off.
Yeah.
Yeah. That was hematology, not you.
Okay. Yeah, I thought you guys did it at some point. So with that, you don't want any anticoagulants, right? So you want to take that along with the glass tubes. Plastic tubes without anticoagulants, then tubes with separator gels would be next, heparin tubes following that, and other anticoagulants, and always EDTA last.
You do heparin before citrate?
Huh?
I'm just talking, sorry.
It's okay. I like speaking out loud. I don't like speaking out loud. I like it when you guys speak out loud.
So why would you take that? Why does it matter if heparin is before like citrate? Because you could use citrate for units. I thought it was the way around.
Was it?
No, probably not. But that doesn't mean I don't think that.
Well, this is what I got from the book, and to be honest, I got no phlebotomy skills except for what I do in mice, and I only used heparinized capillary tubes, or I'd like, yeah, just heparin EDTA is all I ever used. But I didn't use specially EDTA bot tube. I would just use a little bit of EDTA in a test tube and throw the blood in there.
Well, I mean, we didn't use, because citrate and heparin are pretty much interchangeable, but I think they use citrate more than they do heparin. I think it's cheaper.
Yeah, it is cheaper. Because there was the heparin, remember there was a big issue with the heparin coming from China?
Yeah.
So
well,
there's shortages, I think.
Yeah. I remember, for some reason I remember reading about citrate being proper.
I imagine it's cheaper.
Is this the last slide?
No.
We're missing a lot of slides.
I know, that's what I was
We're missing some.
Like the last.
Well, I didn't post this one yet, I don't think, did I?
You did. Just missed the last 5 slides.
I did?
Because it goes from post-collection, Puncture, variation, and transportation.
Yeah, chain of custody, to post-collection, to transportation, sample storage errors. That's it.
Oh, sorry. I'll post this one today. I didn't think I even posted it yet.
They're all open. You can see all of them.
Yeah, but those are the older semesters, right?
Yeah.
Why would you do that?
So you could have them. Huh?
So it's just like one last sheet.
Okay. So we go to separator gel interferences. You don't have this slide. So analytes absorb to the gel. These are some of the analytes that can absorb. Fluctuations, tricyclic antidepressants, and haloperidol. Whole blood, red blood cell enzymes such as A1C, LED, cyclosporin A can be interfered with separator gels. Contaminants within the gel can occur also, so you trace metals, and then preservatives are needed, peptide hormones. Preservatives are needed for peptide hormones, renin and catecholamines, right? Terrible talking. So for sample collection, patients should not have blood drawn from the same side as an indwelling catheter, right? Tourniquet, preferentially not on the same arm. Tourniquets should be released as soon as possible, so don't draw the sample while the tourniquet's there. You get the line, take the tourniquet off, and then draw the sample. Antiseptics should be used and allowed to dry, right? Yeah.
You take the tourniquet off before you start drawing?
Yeah, because you can also blow the vein if you don't take it off. like you try to draw as the tourniquet's on.
Yeah. Yeah, okay, that's right.
So when you stick it in, then you
Undo the,
Okay.
so the pressure like will relieve.
yeah.
You get a, yeah, that's.
Huh?
Do you always use the tourniquet or just the
You always use a tourniquet. You have to.
They tell
because-
you to, but I mean, I've seen people stick with
Well,
the tourniquet.
I mean, if you're like Willie and you've got water hoses sticking, you don't need one. You can literally get them to grip, vena puncture, and tell them to stop, you know, flexing, and then you can draw from that. But I mean, most people, I mean, like me, you could probably do with a light tourniquet. But most cases, it's just easier to use a tourniquet. And you get into a nice little rotation of got a tourniquet, got everything done, I went down like this, and I can just proceed. You know, it's just a little repetition. It's easier. For me, at least.
And I've never done it. I never gave the mice tourniquets.
Oh, I'm sure you probably didn't.
Oh, you can just use a little.
I would heat them up though. I would heat them up, put them under a heat lamp so their tail veins would dilate, and then you can poke them. Makes them easier to see their tail veins.
How do mouse do you do that when it's like all squirrely and trying to
I would give it isoflurane first. Although I have done them while they're awake too, but it's harder, but you have a little special contraption that their tail fits out the back and you kind of smash them in there so they can't move a lot.
I was thinking, wouldn't isoflurane, like, if you were testing for certain things when they're kind of contaminated?
It can, but it's not what I was testing for. It wasn't going to interfere. Plus, it's a volatile organic. It goes away so fast, which was what makes it a great anesthetic, because once you take it away, they blow it off like immediately. So antiseptics should be used and allowed to dry. Only free-flowing blood should be collected. So that goes with your capillaries too. A lot of people, they squeeze and try to push. You're not supposed to do that because you're going to contaminate the sample with your interstitial fluid then, right? So you should only take free-flowing blood. Clenching and releasing will release muscle metabolites. So post-collection causes of variation, right? So controlled more easier by the laboratory, because the laboratory can control things once they get the samples. Criteria for the storage and handling of specimens after the collection is developed by the laboratory. The three variables, right? Transportation, separation of serum from the cellular elements, and the storage. So the lab can control all of those so you don't get as much variation post-collection. Transportation, reasonable delays are well tolerated by most analytes. Blood gas samples are the most affected by handling error, right? Because what are you going to see with long delays with blood gas? Decrease in O2, increase in CO2, because you're going to continue metabolism in those cells, right? And you'll see lactate, ammonia, and acid can accumulate over time due to that metabolism. Proteolysis can also occur unless you have something like EDTA in there that's going to stop proteolysis. And remedies for these errors can include transportating samples on ice, inclusion of enzyme inhibitors. EDTA is an enzyme inhibitor, or they have specific ones for protein inhibitors, like potassium. There's one, not potassium, what is it? I forget. Potassium chloride, I think, is a good but then that'll throw off your potassium levels, won't it? Use of mechanical transporters also. So, those little, you can like put the tubes, and I think they have tubes at North Florida that'll bring samples and stuff. So. Sample processing errors. Serum separation should not be performed until the clotting is complete. So there's a set amount of time before you should do that centrifugation. And that's 20 to 30 minutes. Be sure clotting is complete. Patients receiving heparin may be required several hours for clot formation. Or maybe it'd be better to do serum for a heparin-containing patient. Delay in separation can result in altered metabolite concentrations due to continued metabolism. Platelets release potassium following clot formation, which will cause an elevation in serum compared to plasma. So little things to know. Most analytes will show little change 4 degrees following separation for 2 to 3 days. Some enzymes are labile and will require freezing, and the sample to be preserved, for labile enzymes. And also, freezing with enzymes, you want to minimize your freeze-thaw cycles you're going to do on those also, because every time you freeze and thaw a protein, it'll unfold and refold, and some will fold, form cross-beta sheets and just precipitate out a solution every time. Evaporation can increase sample concentrations, right? So if you leave a sample out without a tube, it'll evaporate and it'll appear like you have an increased concentration of all the analytes that are left behind. For biological variations associated with urine collection, variation is affected by several factors, including amount of water excreted. So the amount of water you take in is going to be the amount excreted unless you have some kind of disease. We measure the amount of water in there based on the osmolality. Who remembers what osmolality is? So an osmol is basically like a mole of substances. An osmolar solution, 1 osmolar would be 1 mole of substances dissolved in a liter of solvent. Do you remember molality? So it's, what was that? The number of moles of a substance per kilogram of solution, right? Versus liter, no, right? Yeah. You don't remember that? Molality? Molality versus molarity. So the molarity is moles per liter. Molality is moles per kilogram.
Kilogram of water.
Kilogram of solution. That's the difference. Moles per liter of water, or moles per liter of solution. Man, I'm confusing myself.
Substance in moles of solute divided by the mass in kilograms of the solvent.
Yeah. So it's the mass of the solvent, and molar is of the whole solution. I always get those two confused. But anyways, remember, the osmolarity or osmolality of a solution isn't based on any one particle. It's based on all the particles dissolved in it, right? So it's the number of particles. If you have a osmole of particles, it's like a whole mole of particles dissolved in that liter of solution. So, and we'll check that when we do our urinalysis lab by looking inside a little thing. You'll see that. Maybe we'll also try the floaty thing. You seen that? Testing batteries. Don't you do that measuring alcohol content in beer?
With a hydrometer?
Yeah, specific gravity. That's basically what you're measuring osmolarity. So.
Yeah, specific gravity that's used for urinalysis.
Yeah. So posture, stress, dietary changes can all affect urine concentrations. Time of collection, like we talked about earlier, and compounds can be unstable in the urine because it's, can be a different pH and whatnot. It's the last one I had. Is that okay? So what was that? We were here for an hour. Huh?